Okay, so I want to show you how to do a power analysis. Remember, the type 1 error is a false positive. Telling a man he's pregnant is a false positive. Telling a woman who's obviously pregnant she's not pregnant is a false negative. You've seen these slides before, but a type 1 error is the mistake of rejecting a true null, and that's alpha. So right over here, alpha. And then type 2 error is here, beta. And so we want to minimize our type 2 error, and so we're going to calculate power, which is 1 minus beta. So we want to see an effect when there is an effect to be found. So you've seen this slide before. We set the type 1 error rate, which is alpha, a priori before. We always go with 0.05 so that we'll accept our result if it's at least 95% certain that it wasn't a fluke. And our beta is the mistake of failing to reject a false null. And so we want to calculate the power of an experiment needed to minimize beta. And the way we do that is we have to do some calculations, and we have to know some things in order to do that. So we want beta to be less than 20%, so we want our power to be at about 80%. And we use the word power because it measures the power to distinguish an effect. I'll show you how to do that. So power can be established by calculating how large a sample size needs to be in order to achieve a power of 0.80 or 80%. So you can go to GPower, which is a free online software. You can go to this website. This UCLA website has a bunch of directions, and it also has this link. So we'll go here and I'll show you that in just a second. So this is the website. You go to UCLA and you can see this is the same link. We click here, and I've already opened it up. It brings you to this website. You scroll down, and here are your downloads. Download GPower for Windows or download GPower for Mac. When you bring up the blank form, this is what it looks like when you click the icon, which I can't show you because it's on my other screen. But this is what it is. It brings it up, and it gives you a power of 0.95, 0.05, 0.3, and it tells you small, medium, large. And here we have t-test, you have exact, f-test, t-test, chi-square test, and z-test, and then you have to pick which one you're going to do, and you can have to pick one or two tail test. Okay, and then when you click this determine, this little sidebar pops out. So I'll show you that in the slides. Okay, I want to take you quickly through a couple of examples. So Marie, a recent biostats student, noticed that her laboratory had changed procedures regarding plasma and wanted to determine if the amount of wastage of plasma in 2019 was greater than the amount of wastage in 2018. She decided to compare the frequencies of plasma wasted to plasma not wasted recorded in her lab during those 2 years. If the plasma was completely used, she coded it as not wasted, and if it had to be thrown out because it passed its expiration date, it was coded as wasted. Her research question was, is there an association between the number of plasma units wasted and year? So we enter the data into the computer like we've done many times before, and run don't forget to weight your cases, and run a chi-square test of independence. So we do crosstabs, we move year to the rows, columns to the wastage to the columns rather. Click display clustered bar charts, click statistics, we can ask for a chi-square, and we ask for phi. Here's our output. She ran the test of independence and found that there was a significant relationship between wastage and year, chi-square of 1 degree of freedom, n equals to 36, 4.02, and her p-value was less than 0.05. Her Kramer's B is 0.342. And when you have a 2x2 table, phi and Kramer's B are the same. So we're just going to report the Kramer's B. So we're going to use GPower now to calculate both the power for both post hoc and a priori. Post hoc is when the analysis has already been run or you already have the data, as in this example. And a priori is when you want to know how big of a sample size we need in order to achieve a power of 8.8. In a priori, I want to show you how changing the effect size changes the sample size needed. So we open GPower, and we select chi-square test. Then we select goodness of fits. We go chi-square here, goodness of fit here. We're going to pick post hoc. We're going to put in all our information from the slide before. I just did 0.3. It could have been more specific and given the full effect size. 0.05, our sample size was 36, our degrees of freedom was 1, and we see that that test that she did had a power of 0.44. Now we're going to change this to a priori, and some of these commands change. We're going to keep that 0.3, even though we haven't done the study yet. We're going to assume an effect size of 0.3 because we did it over here, or we read it in literature. That's the important part, is that you have to make an educated guess, and you must cite where you've made that educated guess from. But we want 0.05, we want power of 0.8, and we'll assume the degrees of freedom of 1, and we see that we need to get 88 samples in order to achieve a power of 0.8. So that's substantially more than what we had. We only had 36. Okay, now I want to show you how the effect size changes the sample size. So G power also, if you look here, it says effect size W, and that's Cohen's W, but we want Kramer's V because SPSS gives it to us, and the interpretation of small, medium, and high is the same for both measures, and it spans from 0 to 1. So we're going to use our V effect size where it says W. We could see, if I started at 0.1 and do everything the same, I need 785 people in order to get a power of 0.8. But if I have an effect size of 0.5, I only need 32. So sample size is greatly affected by the effect size. So let's just kind of go through one of the examples for an independent samples t-test. This is straight from that website I showed you. A clinical dietitian wants to compare two different diets, A and B, for diabetic patients. She hypothesizes that diet A, group 1, will be better than diet B, group 2, which is actually a one-tailed test because she thinks one's better than the other. But the example in that website takes us through a two-tailed test, so we'll just stick with what they did in terms of lower blood glucose. She plans to get a random sample of diabetic patients and randomly assign them to one of two diets. At the end of the experiment, which lasts 6 weeks, a fasting blood glucose test will be conducted on each of the patients. She also expects that the average difference in blood glucose measure between the two groups will be about 10 milligrams per deciliter. Furthermore, she also assumes the standard deviation of blood glucose distribution for diet A to be 15 and the standard deviation for diet B to be 17. Now, all of that comes from the literature of similar studies because we're just best guessing, but you need that information a priori. The dietitian wants to know the number of subjects needed in each group, assuming equal-sized groups. So let's talk briefly about the assumptions, and I keep beating a dead horse here about this because it's so important. Notice that the assumptions that the dietitian has made in order to perform the power analysis. Here's the information we have to know or have to assume in order to do it. The expected difference of the average blood glucose, in this case, she set it to 10. And we need to know the standard deviations for group 1 and group 2. In this case, they're 15 and 17. Alpha is easy, it's 0.05. The pre-specified level of statistical power, that's easy too, we want to get to 0.8. Now notice she didn't specify the means for each group, instead she only specified the difference of the two means. That's because she's only interested in the difference, and it doesn't matter what the means are as long as the difference is the same. Now this is a very busy slide, I understand that, I'm going to take you through it. When you open it up, you'll see this square, and these will be auto-populated. We're going to make some changes. First, we need to fill in our effect size and our power, but we don't know the effect size yet. We have to calculate that. So we know power is 0.8. I think it's auto-populated to 0.95. Alpha is at 0.5, and this has to do with your sample sizes. If your sample 1 and sample 2 are the same size and you divide them, you get 1, right? So this means that we have equal sample sizes. If we do not, you have to do this ratio yourself and input it. And then we select 2 tail tests instead of a 1 tail test. So we do that. This will be empty, this effect size, or it'll be auto-populated with whatever number they put in there. But it doesn't matter yet. We're going to go over here, we're going to click determine, and then this little side panel pops out. We're going to say mean of group 1 is 0 and the mean of group 2 is 10. Now it doesn't matter what their actual means are because this just denotes that the difference is 10. We put in her hypothesized standard deviations, 15 and 17. We click calculate, then we get this effect size, which we then, copy and paste over here. Then we hit calculate. And what we see is that in order to achieve 80% power, if she's going to do this study, she needs at least 42 people in each of her groups in order to get to 80% power. And that's how you do it. It has all the directions in that website, and it's pretty straightforward.